Okay, it's time to go. We kind of wrapped up our DP, dynamic programming lectures, although that will be a constant theme throughout the class. We're going to rely on that basic understanding of what a value function is, cost to go function, how to solve optimal control problems better and better and better. But solving optimal control problems is hard. Maybe let me just make sure I say this carefully. We talked to, I'll give a quick recap of DP just to set the stage for what we're doing today. Dynamic programming. Okay, so we talked about three important cases, right? We talked about the tabular case first. That's where everything was discrete. States were discrete, actions were discrete. We could think about dynamic programming as graph search, or solving an optimal, shortest path problem on a graph, for instance. We talked about the linear dynamics. And a convex cost case. Linear optimal control, LQR being the one we really talked about in detail. And I hope by showing it a few different ways, a few different times, seeing how discounting affects it, there's, I think, seeing that a handful of different ways, I hope gives you more intuition about it and a deeper understanding of it. Last time we talked about approximate dynamic programming with neural nets in particular. And we'll use some of those tools again later also. And the hope, of course, is that, so let's see, the tabular case, if we're thinking about trying to make discrete approximations of continuous systems, then the naive discretization just doesn't scale to very high dimensional cases. The linear dynamics scales beautifully to incredibly high dimensional systems. We can solve under actuation everything, okay? But it only captures the dynamics, a linear approximation of the dynamics, which is great for some part of the state space, but doesn't solve the whole problem. The approximate DP, the neural network version of that, the hope is that it can do some of this sort of mesh, what a mesh could do, but without having to have as many basis functions as, number of bases times to the nth power, or number of bases to the dimension, for instance. We don't want to have the cursive dimensionality. Okay, so there's three sort of fundamental tools, but they really are trying to solve a very hard problem. I think my pages got jumbled a little bit here. Second. Fine. Okay. So, in particular, these things we're trying to find, ideally, J star, the cost to go function. And in general, finding J star is solving some very high dimensional, potentially nonlinear partial differential equation, right? And that's potentially a hard thing to do. So how many people have heard about Lyapunov functions before? Nice. How many people sort of see a connection between dynamic programming and Lyapunov functions? That seems a little less common, maybe. By the end of the lecture, I want you to think about this as I want to give you the tools for Lyapunov theory, so I'm not assuming you know it, but I want you to think about this as a way to make the problem easier, okay? So in particular, if my goal for robotics is not to be, let's say, optimal in every action that I take, but really, that's a pretty tall order, right? If I just want to say I've got a controller that's good enough to get the job done, right? The robot's not going to fall down. The robot's going to accomplish the task. Forgo any chances of optimality, then that should really make the problem easier, okay? And it does. And actually, Lyapunov, even though if you know Lyapunov, you've probably associated it immediately with stability theory. And that is what we're going to talk about, Lyapunov for proving stability. But that is actually deeply connected with optimal control in relaxing the fundamental assumptions of optimality into sort of a just good enough. And I hope you'll see by the end that finding a Lyapunov function can be much easier than finding an optimal cost to go. Okay? So let's do that. So I want to introduce it in the context that it's most famous, which is proving stability of a potentially nonlinear system. Okay? Let's think about how to do that. I'll always go back to my simplest examples first. Simplest nonlinear system was our simple pendulum. Let's say. Okay, got my simple pendulum. The equations, if you remember, are pretty simple. I'm going to write them in this form here. So this is my mass times acceleration. This is my gravity term. And I'm going to separate out the implied forces, or the additional generalized forces, onto the right-hand side, because that'll make things a little cleaner. And in particular, right now, I'll just talk about the one applied torque, which would be a joint friction, right? Damping, if you will. And I'll, of course, take B to be greater than 0. Now, this is one of the simplest nonlinear dynamical systems we'll encounter, but the standard recipe for sort of analyzing systems would be if I give you a differential equation and I give you theta at time 0 and theta dot at time 0, then I could ask you, what is theta at time 10? Right? And even though this system is about the easiest that we can get, we actually don't have closed form integrals for that system. Right? Even if I take damping away, it becomes elliptic integrals of the first kind, and then if you add damping back in, it gets even more ugly, and it's just there's no wisdom to be found there particularly, right? It seems like the wrong question. Being able to say solving for theta of t is just very hard as a function of t, as a function of initial conditions. So we don't want to do that. We need some other way, without explicitly solving for theta as a function of time, for talking about whether the system is going to be stable or not. And for the pendulum, that's why I like this as the opening example. For the pendulum, it's very intuitive that it's stable. So the damped pendulum, of course, we already drew the phase portraits. We know it's going to slowly run out of energy, and the fixed point at the bottom is going to be stable, right? And it's going to be stable asymptotically, for instance, right? But how do we prove it? Okay, here's a simple proposal. Let's write the total energy of the system, right? The kinetic plus potential energy. Kinetic is 1/2 mv squared, right? So that's going to be in the velocity of this point is L times theta dot, so that's what gives me mL squared theta dot squared. That's the kinetic energy. And then the potential energy is going to be mgl cos theta. Okay? And roughly, I want to think about an energy-based argument, saying that if I start with some initial energy, then because I'm a damped system with nobody pushing on me, my energy can only go down. Okay? And the basic structure of the argument is energy is minimal at the bottom, energy is only going down, and so I'm going to construct an argument saying that eventually, as time goes to infinity, I know I'm going to be at the bottom. Okay? And that's going to turn out to be something that's very intuitive and mechanical for the pendulum, but a very general recipe for our nonlinear systems. Okay, so let's do the mechanics of that. stay on this side so it's visually continuous. Okay, so let's think about how I want to think about how E evolves with time, how the total energy evolves with time. So what I want to think about is the derivative, let's say d dt of the total energy. Okay? The energy, let me write it explicitly, is a function of the state x, right, of theta and theta dot. So the derivative of that energy is going to be, it depends on x, but x is changing over time. So the time derivative of energy looks like this, which that's just a vector equation, so I could write out its elements. It looks like this. Okay? I can take the energy and just take the gradient with respect to theta. That gives me what? Theta dot times mgl sine theta. Okay? That's this term. And then this one gives me the derivative with respect to theta dot. I get 2 cancels that, plus ml squared theta dot times theta double dot. Right? So let me write that slightly differently. Let me write that as theta dot mgl sine theta plus ml squared theta double dot. And if you look, this is not a coincidence. It seems like it's a coincidence the way I've done it here. It just happens that this is the left-hand side of the equation I wrote above. So let me substitute in the right-hand side of the equation, and this is just negative b theta dot squared. Okay? Now, b was positive, theta dot squared is always positive, minus of this is always going to be less than or equal to 0. Okay, so that's a slightly algebraic way to realize that energy cannot be created out of nothing. Okay, so that's our first step. Now let's assemble sort of the pieces of an argument. So the first thing we have here is that we know the total energy. And in particular, if we look at the energy, we can observe that it's bounded below. Okay, so this is always going to be greater than or equal to negative mgl. Right? This term is always positive. This term can never go less than mgl, negative mgl. Okay, so it's bounded below, and it's going down over time whenever theta dot is not 0. Okay, so now that's the elements of an argument. Okay, and in particular, we know when it's at the bottom, at the minimum, it's going to be 0. So what's left to prove is somehow that it doesn't get stuck somewhere along the way. Okay, and it turns out that's actually a little bit subtle. So because, for any theta dot equals 0, we have E dot equals 0. But there's only one theta, only at the fixed points can theta dot stay equal to 0. Okay, so let me draw that in a picture here. Okay, so you know the phase portrait. Theta dot, I've got my pendulum phase portrait. Got my equilibrium here. The standard dynamics of this thing is that it's going to run out of energy and circulate and go down to the origin. Okay. Now, where are the places where the energy dot is 0? Okay. It's anywhere that theta dot is 0, which in this case is this picture here. In fact, if you like, this function, this energy dot function, looks like a quadratic form that comes up away from this. Right? Whenever I'm away from this line, I go up. I start increasing. I lose energy faster. Right? And the last observation we need in order to show that it sort of gets to the bottom is that in all the places where theta dot equals 0, it will only be getting E dot equals 0 for an instant. Because the vector field here will immediately take it to somewhere else where it will start losing energy again. Okay? So even though at the moment it crosses this line, energy is not going down. Right? What is that? This is like the robot swinging back and forth, right? At the moment it goes to energy, to theta dot equals 0, at the turnaround point, it's not losing energy at that instant. But then it starts falling again and it starts losing energy again. Okay? You build up that collection of tools, and you can say that as time goes to infinity, I'm gonna get to the origin. Okay, so that's kind of a mechanical systems view of this. Lyapunov theory is basically the generalization and formalization, I would say. That was a loosey-goosey version of the theory, but we can make that all very formal. We can take this notion of an energy function, we can generalize it to systems where even mechanical energy might not make sense, or we want to reshape the energy to accomplish some control task, okay? But we're going to use the same structure of the argument. We're going to try to find functions that are like an energy, that I can say my controller is always going downhill. Right? Like a cost to go function, you try to go downhill on the cost to go function, right? We're going to try to go downhill on some energy function, more generally. And we're going to try to understand the conditions to guarantee that we'll actually get there at some rate, or get there as time goes to infinity, or get there at some rate. Okay, so that's what Lyapunov theory is all about. So if I'm given some dynamical system, x dot is f of x. Okay. Note that there's no control input yet. Right? It's not x comma u, it's just f of x. We'll bring control back in later. This is the closed loop response, if you will. If we want to prove stability at the origin, and if you don't like proving stability at the origin, then change your coordinate system so that the place you want to prove stability is the origin. So that's not a loss of generality there. Okay? And let's do this by constructing a differentiable function we'll call it v of x, such that, for simplicity, I'll make v have to be 0 at 0. Okay. And I'd like v of x to be positive everywhere when x is not equal to 0. And then I want to have say something about its derivative. I'd like v dot at the origin to be 0. I'd like the origin to be a fixed point in that Lyapunov energy function. Okay. And then I'd like to say I'm going downhill. Okay. The shorthand, so I wrote out explicitly the 0 case and the greater than 0 case, right, in both of these. But I'm not going to keep writing that. There's a shorthand that we're going to use that is commonplace. For a quadratic form, if a matrix is positive definite, then its quadratic form is 0 at 0 and positive everywhere. And we're going to use the same notion of positive definite function for this. We're going to call this a positive definite function. If it has that property, and we'll use the same notation that we've used for a matrix. We'll say v of x is this kind of that symbol greater than 0. Positive definite function is positive everywhere except for the origin. 0. Okay? And then this one will be a negative semi-definite function, right? Okay, so every time I write that positive definite notation, I mean both of these conditions. So if I can construct a function for which these conditions all hold, then that is actually sufficient to prove the stability of the fixed point at the origin. X star is stable. Remember, we had a bunch of definitions of stability in the lecture that I didn't get to give, but in the notes in what you read, is stable in the sense of Lyapunov. Remember stable ISL? In the sense of Lyapunov. Okay, that's not a coincidence. Lyapunov, and this is what we're calling the Lyapunov function, V, right? This is why, in fact, that got the name in the sense of Lyapunov. Okay, and that sort of maybe intuitively makes sense based on this energy argument. It's the same kind of structure, yeah. So stable in the sense of Lyapunov is a local stability. Comment? If I start talking about global stability, then I'll have to talk about radial unboundedness. Good question. Right, the sense of the stable in the sense of Lyapunov is, actually, I guess I'll do it. If you remember what stable in the sense of Lyapunov function means, stable ISL is there exists an epsilon greater than 0. Sorry, for every, for all epsilon, there exists a delta greater than 0, such that if I start inside the delta ball, that implies that for all time, I'm inside the epsilon ball. Okay, now we're going to understand this in a picture that this kind of weird ball notation. It sort of sounds arbitrary. It's a very general principle, but it makes perfect sense once you have the concept of a Lyapunov function. Okay, so let's imagine I have some other phase portrait. Let's say I've got just x1 and x2. Okay, and I found some positive definite function on this. So coming out of the board, I have some positive function, and I'll draw the level sets of that function. Let's say I've got the level sets. Maybe this is v equals 1. Maybe this is v equals 2, and down here was v equals 0. Okay, so I've got some function growing out of the board. What does this argument mean now? Okay, so I want to give a guarantee that that x for all time is inside some epsilon ball. Okay, so if you come up and pick an epsilon, where epsilon is implied to be small, which is why I don't need radially unbounded, right? You come in and say, here's an epsilon ball. pick, the task is now you need to be able to pick a delta ball that guarantees that the system will never leave that delta ball, or the epsilon ball, sorry. I'll take one more color here. How do I do that? Well, it turns out that the Lyapunov functions, if I know that v dot is always going down, or v dot is always negative, that means v is always going down, and I have some sub-level sets of v here, then you know if I started inside some region here, okay, I'm never going to go to a place where v has gotten bigger. So if you tell me I need to find some set of initial conditions so that I stay inside this ball at all times, then I can look for some sub-level set. It doesn't have to be round or anything like this. I've got some sub-level set that fits completely inside there. Okay? If this is v equals, I don't know, v equals 0.82, fits completely inside that ball, then any initial conditions that start with v at 0.82 or less, if I have those properties, are guaranteed to stay inside this epsilon ball. Yeah? So in order to play this game of stability ISL, I just need to pick another ball, delta ball, of initial conditions that somehow make sure the entire ball has v less than 0.08, 0.82. Yes?
Can the outer ball also be non-circular and like oval shape?
Right. So
Just the inner ball.
the value function, the Lyapunov function could have arbitrary contours, okay? And the fundamental concept is that you don't go up in Lyapunov value. The statement of ISL is in the coordinate of balls. And so the exercise we're doing here is basically to map balls, in space into the coordinates of Lyapunov and back. So both the delta and the epsilon are specified in terms of circles, in some norm. Okay. So the game I'd have to do is somehow find some circle that is fully contained inside the sublevel set, such that any initial condition here, it might walk around inside that sublevel set, but I know it's not going to leave that sublevel set. Therefore, it will never leave the epsilon. So that's my delta ball. Did I say that well enough? This is how you communicate stability ISL if you don't have the concept of a Lyapunov function. You can convert everything into circles and not have to introduce some new function that doesn't exist. Okay? But the way you actualize that is by actually finding some function v, like the mechanical energy of the pendulum, that can allow you to prove that this sort of thing exists. Okay, so similarly, if I took the energy function of the pendulum, just to make it play the game, I could say that v of x is the total energy of the pendulum, and maybe I'll add mgl just so that it's 0 at 0. Okay? Because I have that E dot is strictly less than 0, and 0 at the origin, I can say that the origin of the pendulum, the downward fixed point of the pendulum, is stable ISL, using the Lyapunov machinery. Yes?
So let's say they're close to the origin, you have
Yep.
then if I was to try to pick an epsilon smaller than that radius, my delta would have to be
Great. So those are exactly the types of exercises I want you to be doing in your head. So why can that one not happen? There must be something in my statement, right? So I said that v is only 0 at 0. So you're not allowed to have an epsilon ball that has 0, right? So that one's ruled out. So that means there must exist some delta inside here. I assumed everything is differentiable, right? So that the function has to go from 0 to this level set and go through all values in between. Okay? So if there was an epsilon ball, then there was a smaller delta ball that has to fit inside there. Mm-hmm. It turns out, So the pendulum we know is not only, the damped pendulum is stable asymptotically, not just stable ISL. Okay? We've only shown so far a Lyapunov argument for proving stability in the sense of Lyapunov. But the name isn't limiting. You can actually prove asymptotic stability, you can prove exponential stability, all with Lyapunov functions. Okay? If you can find an energy-like function for the system, right? What I didn't do here is because this is my abstract x dot equals f of x, I didn't tell you how to find v yet. I'm just saying, like we said for a cost-to-go function, the Bellman equation is just a sufficiency theorem. If you can produce a cost-to-go function, then you know it's optimal. Here I'm just saying if you can produce a v, I can tell you that it's stable. We're going to work later on algorithms for coming up with v for you. Okay? But right now, if I equip myself with a v, how would I prove that a system is asymptotically convergent to the fixed point at the origin? The problem, you see, the thing that's limiting here is I said that v dot has to be less than or equal to 0. But if v dot was 0 for a big swath, it could just hang out there and never have to actually converge. Okay, so the intuitive thing we're going to do, which is exactly the right thing, is we're going to turn this from a less than or equal to 0 to strictly less than 0, saying that energy has to be constantly dissipating. And that means we actually have to get to the origin. Right? I want to find a v of x greater than 0 and v dot of x less than 0. The change was right there, right? That's it, and that's a strong enough condition. There's a couple nuances there. Maybe this is a good time to address Adam's question. Okay, so we can use a Lyapunov function to talk about local stability, and just say if I have a v that's valid, it satisfies these conditions just in some sort of small neighborhood of the origin, that's sufficient for local stability. If we want it to hold for all states, then we have one other extra condition, okay? We could talk about global stability. And global asymptotic stability. The cool kids call that gas. Okay, really? Like you'll see it in papers all the time. You're like, what's gas? Okay. It's global asymptotic stability. Okay. That requires one extra condition. You want that the limit as x goes to infinity, v of x also goes to infinity in some norm. You want it to be radially unbounded. And there are some special cases that you can come up with counterexamples of systems that if they don't have this property, v dot can go downhill, but you can escape to infinity faster than your v dot is decreasing. It's a little bit like an analysis kind of game or something, but you can construct systems that can escape to infinity while having v dot go to 0 and satisfying the rest of the conditions. You just have to take away that weird case. And then you can say things so global stability means that for all x's will converge to the fixed point, right? Or you can talk about regional stability. Which satisfies the conditions in some domain that contains the origin. See, they just, if you draw some domain D that contains the origin, D for domain, okay, then you could talk about some sort of regional stability. And we'll use that a lot, actually, to think about regions of attraction and other important concepts. Most of our robots are not globally stable, right? Atlas is awesome, but it's not globally stable. Like, you could come up with initial conditions that it'll fall down, right? Including the falling down condition, right? I mean, and there's probably initial, I mean, maybe Atlas can always get back up. That would be closer to being global stability, but I don't know if I dropped it from 100 meters, it's not getting back up, right? And that's part of our end. So. Okay, so we have stability in the sense of Lyapunov. We have asymptotic stability. Both just given a v, I can do this. So the natural question would be, could I also get exponential stability? That was sort of the last of our nonlinear fixed point stability concepts. Can we do exponential stability? Turns out you can. If you find a positive definite function. So what was the difference, remember, between asymptotic stability says, I'm going to get to the origin as time goes to infinity, right? And so just going downhill is enough. But exponential stability says I'm going to converge to the fixed point at some rate that is bounded by an exponential. So in order to get that, we're going to want v dot not just to be less than 0, but to be strictly less than, bounded away from 0, right? So I'm going to say that v dot of x is less than. It turns out the right thing to do is to have a relative bound like this. This is still in the sense of a positive definite of a function. I could say that v dot plus alpha vx is a negative definite function. Why does that work? Well, then that implies that if I have some initial condition, some initial value of v, then the rollouts of this are going to be bounded by the initial value of v, e to the negative alpha t. This is for alpha greater than 0. If we have this first order system, if you just think about this as x is less than negative alpha x, then we know that x is going to go downhill like this. And that's also true of v. Okay? So that allows us to put a bound on the exactly the exponential stability sort of bound on the convergence rate. Okay, so I gave you kind of a mechanical intuition about energy, and then I gave you a few definitions. Now let's try to make it more intuitive. Yeah, please. Yeah, this should be less than or equal to, I think. That's right. I should have used the same there. Yes, in both those cases. Thank you. Does that kind of make sense? So the magic, of course, is going to be finding these functions b. Okay, but it turns out what I want to convince you, again, just to say it multiple times, but finding a cost to go function is hard. Finding a value function is going to be easier. Or the Lyapunov function is going to be easier. Okay? That's the promise. All right, so let's just exercise that a little bit here. So let's take the simplest linear system. X dot equals negative x. And let me propose a Lyapunov function x squared. Let's just think about this. Okay, so I do my Strogatz style plot the first order system, right? And then this thing just looks like a line of slope -1. It has a fixed point when it crosses the origin, right? And the values of the derivative of x dot are positive over here, and they're negative over here. So I'm pretty sure that's going to be a stable fixed point. But what can I say about it using the Lyapunov function x squared? That's the question. And I'll take the chance to do it this way. If you could just plug that in. Is the origin stable ISL? Is it asymptotically stable? Is it exponentially stable? Okay, what do you think? V dot of x, I can just run the mechanics. I get 2x for the partial v partial x. Put my dynamics in for this. I get -2x squared. That's what v dot's going to be. That is a strictly negative definite function. It's 0 at 0, but negative everywhere else. Yeah. So that means it's going to be good enough for stability in the sense of Lyapunov, yes. It's also going to give me asymptotic stability. Right? This, if you have this condition, you certainly have the ISL condition. And it also even has this condition, because x squared is this. So if I choose alpha to be anything, if I choose it to be 2, then I've proven exponential stability. Yeah? Cool. Yes? That is true. The converse is not true. Let's see. If you it's the same thing we had a conversation about the other day. So if you have indeterminate linearizations, for instance, you can get things that break some of the simple hierarchies. But this is true. It's true. Yes. So if you're exponentially stable, you're asymptotically stable. If you're asymptotically stable, you're stable in the sense of Lyapunov. Mm-hmm. Good. Okay. Let's do something more interesting.
In that case, it's globally stable, yeah?
That's true. It's also radially unbounded. I should have added that to my question. Linear systems, that was a linear system, right? So linear systems can only be, if they're stable, they're globally stable. They can only go to stability to the origin or unstable. Or marginally stable, right? Okay, here's still a 2D example, but or a one-dimensional flow, so I can draw everything. let's do this one, negative x plus x cubed. Okay, what does that look like? If I plot this, x versus f of x. Right, so around the origin, this thing looks like negative x, okay? But as I get farther, it's going to look more like x cubed. Yeah, sorry. Yeah, dv dt is going to be, since v is a function of x, right? It's partial v, partial x, times x dot. Right? The dependence on time is not direct in my v, it's only through x. And x dot is f of x. Yeah, of course, yeah, good. It's good to ask. Okay, so this thing looks like negative x near the origin, and then it looks like x cubed later. Turns out it goes up like this, something like this, okay, and it happens to cross at those 3 points, and a little bit of algebra will tell you that the point it crosses at is 1 and negative 1. If I do my Strogatz analysis here, it's above the line here, it's below the line here, it's below the line here. Okay, so this one's going to be a stable fixed point. And now I want to think about a Lyapunov function that might be able to prove the regional stability. In fact, I want to even say something about the region of attraction of this system, right? So all initial conditions, so x star equals 0 is a fixed point with a region of attraction. Hope you remember the region of attraction idea, right? So all initial conditions that are inside negative 1 and 1 will eventually get to the origin. The cool thing is we can use a Lyapunov analysis to get that region of attraction. Okay? If I can find Lyapunov conditions that are satisfied over some domain, which I'm going to want to be this domain, okay, then I can talk about stability over a domain, and I can say something about the region of attraction. And I should not be able to find a Lyapunov function that is valid outside that domain. Okay, which is sort of logical because x dot is going to be 0 here, so v dot is going to be 0, so clearly I'm going to violate any strong Lyapunov conditions. Okay, turns out v of x equals x squared is strong enough again to do it. Which is nice, because I'm not pulling these things out of a hat. It turns out the example I gave you last time, the negative x, we know how to find Lyapunov functions very easily for linear systems. The linearization of this system at the origin is actually negative x. Okay? So this is a candidate I can get by just linearizing the system at the origin and using my linear Lyapunov function to propose this. Okay? And that's often going to be true. If you do the math then v dot of x is going to be, I'll shorthand it for you here. X squared is going to be 2x squared minus 1. So this function is 0 at x equals 0, 1, negative 1. Those are the roots. It's greater than 0 for all x greater than 1, and it's less than 0 for all x except for x equals 0. Okay, so what I have is a function here, a quadratic function. Okay, and the evolution of this system says this function's going down. The value of this is going down whenever I'm inside here. Okay, but as soon as I'm here, the value of that system is going to go up. That value function is going to go up. Makes total sense. Now, here's a key step, okay? Any sub-level set, this is what the argument we used already, any sub-level set of V is going to be an invariant set, okay? It means that if I start inside that set, we know V is never going to go up. So I can say that if I pick some positive rho, a scalar, okay, is an invariant set. If you go into that set, the dynamics will never let you leave, right? It is invariant. Okay, and so basically the argument here is that in this domain, the set that is V, actually V of X, so regions of attraction are always open sets because their boundaries are determined by separatrix and these manifolds, okay? So the set here that's strictly less than rho here, the conditions are satisfied over that entire set, and this becomes an invariant set, and it is inside the region of attraction. How do I get that? So I know that I'm never gonna leave that set because the conditions hold over this. Let me say specifically V of X less than 1. I mean to say rho there. That's strictly less than 1. Okay. Over that set, I know that x dot is less than 0 except at the origin. Okay. So I'm never going to leave that set, and in fact, I'm going to converge asymptotically to the origin. That means every initial condition in here is inside the region of attraction of that fixed point. Yeah. Invariant means you're never leaving it. So we get that. So any sublevel set of a valid Lyapunov function is an invariant set. Yeah. There are other ways to find invariant sets. Any fixed point is an invariant set, for instance. But Lyapunov gives you an easy way to carve out invariant sets. Yeah. I will give you the full machinery of that later, but it's actually a lot like solving an LQR problem. There's a Lyapunov condition, which is a Riccati kind of condition, or it's called the Lyapunov equation, that will produce those. So the same kind of machinery we had for LQR, we're going to have that for Lyapunov. Good. Yes? It's still, yeah, so if you're less than or equal to 0, that means V will not go up, right?
But it can still go to a higher sublevel. Or like an outer sublevel.
Right, there's some trick. I'm going to draw in just a second the, I think I know where you're coming from. I think what I said is correct. So if I'm inside this set, I will never leave it. That's true, right? Because I know V is never going to get bigger, right? There's another condition about the V dot sublevel sets, which is more subtle. You can leave if you're not inside an invariant set. I think that's probably where you're going. That's a slightly different condition. This is just saying simply that if I know the energy is 5, and the energy is never going up, then I know the energies less than 5 set is safe, is an invariant set. Okay, so the general form of that in ROA sort of statement. Give it an example, but let me make it just a little bit more explicit here. There was a 4 somewhere. This should be a 2? Okay.
I'm trying to figure out where you get the 4.
Okay. No, you might be right. So I would have thought this was going to be 2x squared and then negative x. Oh, you're right. I just did that wrong, didn't I? Negative x plus x cubed. Yeah, that should just be it. Yep. And I wrote it again here. I don't know where I pulled that 4 out of. I had. Yeah. This is 2x, no, like that, right? And then this should be, oh, that's what I did. That's weird. I permuted the 2 and the 4, okay. That's pretty weird. All right, the general form of that, thank you for catching that, is if I have a v of x greater than 0, v dot of x less than 0, for all x in some sublevel set, where rho is a positive number, then I have, for initial conditions that are inside that sublevel set, it implies that as time goes to infinity, v goes to 0, yeah? And therefore, also x goes to 0. Yeah. Region of attraction. Right, so every fixed point has associated with it, every stable fixed point has associated with some region, which is all of the initial conditions that will eventually arrive at that fixed point. That's the region of attraction. All right, so again, you should be asking yourself these questions like, why can it not do, why could I never get stuck in a local minima, for instance? That's a good question, right? So could this, like if I had, what if I had this? Then I could have, and if I found something that was, for all rho, let's say, this. Like, so what's preventing me from getting stuck here? I'm saying I'm not converging asymptotically to there. Yeah. Right, so at this point here, the dynamic, since partial v partial x equals 0, that would suggest that v dot is equal to 0. And that can't happen because I said it was strictly less than 0. And that's exactly the difference between asymptotic stability, which requires this to be strictly less than 0, means local minima can't happen, versus stability in the sense of Lyapunov, where that could happen. Potentially I could get trapped. I don't have to actually get to the origin. Okay, so that's true. And furthermore, this set, x, where v of x is less than rho, must be inside the region of attraction. there's a true region of attraction. In the example before, we got it exactly with our Lyapunov function. I can't from these statements say I found the biggest region of attraction. I'm just saying that this Lyapunov function proves that the region of attraction is at least as big as that sublevel set. Okay, so maybe let me draw the picture that I think Lyapunov was thinking of here. Correct me if I'm wrong. But so let's say I have, now this is 2 dimensions, so I'm going to draw my v's out of the board again. Let's say I have here v dot of x is less than 0 inside here. I find some swath of space where v of x is less than 0. V dot of x is less than 0, and I've got level sets. This is like v equals 1, v equals 2, v equals 3. Okay, so I've got some Lyapunov function, and I have some downhill conditions. Okay, so the trick is, so V2 is an invariant set. Every sublevel set is an invariant set. So if I start inside here, I know I'm not going to leave the green region because I've got v dot less than 0. But there are places, for instance, if I started here, even though v dot is less than 0, right, it could do anything. I don't have necessarily a guarantee that I'm going to stay inside this. I mean, if v of some other number could be very, very big, the only thing I can say is that inside some invariant set, if v dot is going to 0, then I will converge. Right? But once I leave an invariant set, I can actually, I can't say anything. So that really is a coupled condition about v dot being 0 over an entire invariant set. It's important that this is an invariant set. If I just told you that, if I instead, let's just say a counterexample, this would be wrong. If I said that v dot of x is less than 0 for all x, let's say x squared less than 1, that doesn't tell me anything unless I know x squared is also an invariant set. You can have v dot go down, but if it leaves the set, then it could go to a place where v dot goes up again. Yes?
If you know what your
Yep. I think you're right. I think if you have the extra machinery of the Lyapunov function and the sublevel sets, you probably aren't talking about delta and epsilon anymore. The delta epsilon language is to give you a form you can work with without having to fully define Lyapunov functions. Good question. Yes. So I know that v dot x is less than 0 here. But I could have v dot going down, but then I could go to a place where v dot goes up. Right? So if this white region is the place where v dot's going down. But if I don't couple that also with some other argument about invariance, then I could go, v dot could be going down, but I could go to a place where v dot goes up. I feel like it didn't come out quite as clearly as I wanted, but I think that's good. You want to be, and invariance. Because if v dot is less than 0 instantaneously, but it can in the future obtain v dot positive, then you've got nothing. Right. So because of this, I know that if I say for all x where v is less than rho, then I have this additional thing saying v is never going to go less than rho or greater than rho. And for all of those values, I'm going to go down. So putting those two together says that for all x, since this is invariant, I will never leave, and I will always go downhill. If I only write this, then in my mind, I don't have any statement about, like, once it leaves this, then v dot could be doing anything. V dot could just explode to infinity. You know, v could explode to infinity. I've got no guarantees. This, as stated, is only making a claim about what v does over some set. Yeah.
But so in practice, wouldn't you use v dot smaller than 0 to find your invariant set? Like, how else would you find the invariant set?
You use the coupled conditions of v dot and v, but it is the point I guess I'm trying to make is that it's not the v dot equals 0 set that's your region of attraction. It's the v set that's your region of attraction. V dot alone is not enough. You could go to a place where you're going up. So yes, you use those to find the thing, but the region is defined as a sublevel z of v because you need it to be invariant. It's good. I appreciate when I say something not clearly, you should ask questions, and I appreciate it. Okay, there's maybe one other just thing to throw out, which is, in fact, I'll just say that there's an additional step, the thing we talked about in the pendulum, of I can have v dot equals 0 instantaneously, but I leave it, and so there v dot will still go down 0. There's a thing called Lassalle's theorem that I will only mention here that can strengthen this a little bit. Lassalle's theorem allows you to take an energy type function, a Lyapunov function, that is only less than or equal to 0, but in some cases still say that something is asymptotically stable. It's just a slightly stronger condition. But in the interest of time, let me not emphasize that in its full glory and make some other connections. Okay, here's the punchline of the lecture today. Okay? I want you to understand how Lyapunov functions are related to cost-to-go functions. Okay, so let's write the continuous time Hamilton-Jacobi equation. So I have some loss function, okay? I have partial j, partial x, f of xu. That thing has to equal 0. That was the Hamilton-Jacobi Feldman equation in continuous time, right? Let's unpack that a little bit. So first of all, the Lyapunov is not for systems with inputs, right? So let me examine this system for this is a star here, okay? Let's plug in the optimal controller into this so that we have a closed loop system. Okay, so then my conditions, and we did this once before, are just okay. Let's write this a slightly different way. This thing here is just dj dt, right? J dot. So really what I want you to see in this equation is this is actually j dot of x equals negative Lx u star. That's how we want you to read this equation. And we did that a little bit before, right? So that the time derivative of the cost to go function, it has to be decreasing at the rate that my cost is being accrued instantaneously. Yeah? Yes? Yes, thank you. Thank you. Let's compare that with our Lyapunov conditions, which the key one here is that v dot of x is less than or equal to 0, or let's call it less than 0, okay, for the asymptotic stability. When L is positive everywhere, it's a positive definite function, then a cost to go function is a Lyapunov function. That part's kind of clear. But here's the important thing. This is like a relaxation of that. It's so there's one solution to this. There's a unique solution to the partial differential equation in the high dimensional space that gives me that matches everywhere this derivative condition. Right? And it's hard to find. And we do dynamic programming and we do neural network approximations and we do all this crazy hard stuff to find this one true function. It's way easier. There's a million functions that satisfy this condition. This is a relaxed version of this. The J star is one choice, but there are many, many more choices. I did x squared. Like simple functions can often prove stability of the original nonlinear systems. The optimal cost to go could be very complex. The Lyapunov functions can be very simple. Okay, and there's all kinds of ways to sort of play back and forth between these two. When we do control design with Lyapunov, there's versions of this where you try to find, I'll save that a little bit. But basically, you can walk back and forth between these. You can try to find something that's less than or equal to L of xu, for instance. You can relax that explicitly. But what we did today was just less than or equal to 0. That's the simplest case of understanding the stability criteria. So think of this as a relaxation of Lyapunov, of the optimal control conditions. Now, I've given you algorithms for optimal control. I haven't given you algorithms for Lyapunov, but that's what next lecture is going to be. It turns out, so we knew how to pull the control out of if we have a cost to go function, we could extract the minimizing u and we have a policy. Right? I haven't given you that for Lyapunov, right? And it's a little bit more, since this is just a function of x, we have to think a little bit more about what that looks like. But you can do that. In fact, that's kind of what people did for a long time in nonlinear control. They would use Lyapunov type arguments to design controllers. So I'll just end by giving you one example of that, which is a particularly simple, clean version of it. So imagine we want to do the swing up for the pendulum. Okay. Okay, so if you remember the pendulum problem we want to get to this fixed point. Okay, we want to stabilize the system. There's a particular orbit here. This is theta versus theta dot. There's a particular orbit here, which is the one that visits the unstable fixed points. It's called the homoclinic orbit. So here's my idea for well, it's not my idea. Idea that I will present for an energy shaping kind of control for swinging up the pendulum. I'm going to construct a Lyapunov function who obtains a minimum on the orbit, on the homoclinic orbit. Okay, I'm going to make a function that is 0 along that whole orbit and goes up everywhere. And I'm going to come up with a controller that has v dot going down, which means I will converge to that orbit and ride it into the the unstable equilibrium. Okay? It turns out that's actually pretty easy to do. So the homoclinic orbit is just defined as it's all of the states that have energy MGL. That's the energy of the upright. And these are, in the undamped pendulum, these are the lines of constant energy. So I'm going to say that this is my desired energy. And I'm going to come up with a Lyapunov function, which is just, I don't know, call it 1/2 actual energy minus the desired energy squared. Okay? If I use error notation, error coordinates, I'll say this, I can just write this as 1/2 E tilde squared. I see this as basically taking x squared as my Lyapunov candidate. Okay? It's a little bit more subtle because of the shape, but that's still fine. The dynamics of the pendulum, of the forced pendulum, ml squared, theta double dot plus mgl sine theta equals u. I chose u before as b theta dot, but in general, this is where my torques come in. Okay. E tilde, so E dot in this is just u theta dot. If I take my derivative of my mechanical energy, just like I did before, and that's consistent. Before, I remember I got negative b theta dot squared, and that's also just, many of you know, that's just torque times velocity is the rate of change of energy, right? Okay, so E dot is this. E tilde dot is E dot minus E desired, so that's 0, is just U theta dot. So here's my proposal for a controller that doesn't use too much torque. We'll take a torque limited case, but which makes my Lyapunov function go down. Okay, super simple. I'll just say U equals negative K theta dot. Oh, E tilde, sorry. For some K greater than 0. Why? Because now my Lyapunov function is going to be the derivative of my Lyapunov function. I'll just write it down here if that's okay. I just wanted E dot to look like E tilde dot is going to look like negative K theta dot squared E tilde, which is a positive. This is positive, so this thing is negative. This looks a lot like my Lyapunov, exponential Lyapunov conditions. Okay, so by just looking at proposing a Lyapunov candidate, and then proposing a controller that makes that clearly negative, I can come up with very elegant, simple controllers that can achieve complicated things, right? So it's a few lines of code. There's no computation involved. It's beautiful. It turns out if it's a robust controller, if I have the mass wrong by a lot, it still works. You know, I didn't have to wait for value iteration to converge. This is my controller, negative K theta dot. I have a proof that it gets to the top, and it's like super simple and good. Okay. So I think it's important to we're going to use the optimal control tools a lot, but asking for actually optimal controllers is sometimes too much. You can often get away with a lot less, and our algorithms will go farther with more proofs, less. Lyapunov functions are used even today, like the neural Lyapunov functions, neural barrier control barrier functions you might hear. This is actually the stuff that people use a lot in assured autonomy. If you want to prove that your neural network-based controller isn't going to make your car crash or whatever, people are very much using the machinery of Lyapunov barrier functions to prove that. Okay, we'll develop it a little bit more in the next few lectures, yeah?